So this is, I opened up a page of the book. This is the question that was posed before about the effect of this parameter, the threshold 1 and the threshold 2. I said, here in the results that I showed, we use 0.1 and 0.5, but if you look at the difference, which would be this case, the black is the tensile twin, the red is the compression twin. The full curve would be the twin fraction, the one that you would measure. The points curve would be the effective twin fraction, the one corresponding to the grains that reorient. If you use 0.1 and 0.5 here, you see that it starts below, but it catches up very, very quickly. The same with the compression twins, it catches up very quickly. If I use 0.1 and 1, yes, it takes a bit longer to catch up because I make this much higher, the threshold. Instead of 0.5, I put 1. But eventually it catches up. If I use 0 and 0.5, you get that. If you use 0 and 1, you get that. So it's a second order effect, really, changing those in a wide range. So it doesn't really change much the results of your simulation using different values. What really matters is the fact that you keep your effective twin fraction as close as possible to the measured twin fraction. The one associated with the shears. Okay, so we were here, and this concerns the activity then of the different systems and how it evolves. By the way, I forgot to mention, in this example, we run 20% in plane compression followed by a calculation of the yield surface. I'm going to be showing the yield surfaces now, but in the activity file and also in the stress-strain file, you will also have the stress and strain rate states that correspond to the calculation of the yield surface. And so here, and that is very interesting to analyze, in this yield surface, 72 points were used. So every 5 degrees the material was probed with strain rates, every 5 degrees over a 360-degree circle in the sigma 1, sigma 2 space, and each of those points, of course, is a completely different state of stress, and so it activates completely different combinations of systems. And so if you look at that file, the activity file, the part that corresponds to the yield surface, which is next to the one that corresponds to the in-plane compression, it lists the relative contribution of each mode to each of the points in the yield surface. Then you can see in a 360 degrees. Let's say that your yield surface is like that. You can see at each point which are the systems that were activated, or what combination of systems was activated to provide you each of these points of the yield surface. That is what is here. And for example, you can see here that the mode 1, which is the prismatic, it tends to be very active always, because it's the softest mode. But for example, the tensile twins, they show a large variation here. The tensile twins go 0.37, 0.42, 0.16, 0.22. So this is also a very important part of information to see how your material is accommodating strain. Okay, I talked about the yield surface. Well, here are the yield surfaces that you should be calculating if you run the examples. Now, the one at the center is the initial yield surface for the initial values of the Boche coefficient before we started the forming. And the first thing that you can notice, well, because this texture has orthotropic symmetry, the yield surface is fairly symmetric, but tension in the direction 3 has a lower yield point than compression in the direction 3. That is because in one case you activate tensile twins, which are easier than the compressive twins. Now, you start the forming, and after 20%, you recalculate your yield surface, and depending on what you do, you get very different results. For example, let's look at through thickness compression, which is the green one. Essentially, in through thickness compression, you activated compressive twins. This is what you get for the yield surface. In through thickness tension, you get this, and these are the real values of critical stresses. The material has been hardening, and so these are real values of critical stresses. This has to do with a lot. In all the cases you have 20% strain, but this has to do a lot with texture hardening. So depending on how the grains reoriented, this yield surface can require much higher stresses just because the grains are not reoriented with the easy systems to accommodate stress states that corresponds to these points. And then this is a bit of an oddity, the black one. The black one corresponds to in-plane compression, which is the problem that we just looked at and solved, and it breaks the orthotropic. You'd expect that if you do in-plane compression on this texture, you're not going to break the orthotropic characteristic of the texture. You are still keep that symmetry. These pole figures being orthotropic, but in reality you do break the orthotropy. This is what happens after 20%, and this has a bit to do with the fact that the way we reorient our grains, we don't force the grain to reorient in order to keep the orthotropy of the yield surface. So because the distribution of grains is not orthotropic, then when you test this texture you probe this texture for the yield surface, you get a black curve which is at an angle. So I'm not going to go beyond that. I just wanted to show you what is the result of calculating yield surfaces with this approach. So the last part is looking into twinning statistics. I'm showing here, I'm going to go slowly, but I'm showing here statistics that correspond to through thickness compression and through thickness tension. And the idea of showing this is that it allows you to compare a system where the tensile and the compression twins are simultaneously active in your material. So that's why I show this. These are the files twin Schmidt stats and twin variance stats in your run. We run the Monte Carlo assumption for twinning. We did 20% through thickness compression, 20% through thickness tension. We plot frequency distribution and volume fraction of tensile and compressive twins as a function of the Schmidt factor and as a function of the variant activated as a function of also the Schmidt factor. I'm going slowly here. So what we see here is that, let's look at the tensile twin first. If we look at the tensile twins, the Schmidt factor typically goes from 0 to 0.5. In reality, it can go a bit off those values because the Schmidt factor that goes from 0 to 0.5 is defined only for a tensile test, that is done on with one single system being activated. Our definition is a bit more general, so it can go a bit beyond that, but not much beyond that. So what you see here is that for the tensile twins, the black bars show that the frequency of this is the volume fraction. This would be the volume fraction of grains that have twin after the 20% deformation, and those grains are not the ones with the highest Schmidt factor, but are the ones with Schmidt factors of the order of 0.4. However, for the compression twins, most of the volume fraction are for grains that have a high Schmidt factor. The other interesting piece of information is, okay, what are the twin variants that corresponds to these grains? Because this is not telling us variance, this is telling us Schmidt factors. But if you look at the variance, in the case of tensile twinning, most of the twins, nearly 90-some%, are from variant 1. So you activated mostly twins from the variant 1, and you activated very little from the variant 2 and very little from the variant 3. By the way, the lines here, these square symbols, that corresponds to experimental data. But if you look at the compression twins, activated about 70% of variant 1, but they activated about 30% of variant 2. The compression twins, and a bit of variant 3. Now, in the case of through thickness tension, you can see that variant 2, variant 3, and variant 4 are activated, and they are a non-negligible volume fraction of twinning. So, using the predominant twin reorientation scheme, all the twins would be on the first column, because you always pick the ones which are the highest variant. But as you can see, the experimental data shows that they don't have to be the twin with the highest Schmidt factor. So the experimental data shows that all these variants are possible for this particular condition. Okay, so these statistics take some time to digest, but they give you a lot of valuable information and information that can be compared against EBSD-based statistics on twin analysis, and we have used them in that way. Now, the files that were used to calculate those histograms or bar diagrams are the files twin Schmidt statistics, and this is the statistics only for the mode 1, which is the tensile twin. There is a similar one for the mode 2, which is the compression twin. And the twin variant statistics, once again, this is for the twin mode 1, which is the tensile twin. So what you see here is different values of the Schmidt factor, which is this one, 0.17, 0.22. Essentially, you divide the horizontal axis in cells, and you do a statistic counting how many points fall in each cell, and that's your statistic. So the center of the cell is 0.17, 0.22, 0.20. So this is the interval to which of the Schmidt factor, and these are the values at the beginning, and these are the values at the end. These values get accumulated, and what you have here is the number of grains that have been reoriented. So at the beginning you start with 0, then you have 86. I don't know what happened here with the 2. The 2 I must have erased it, but it goes from 1 to 3. But for the last two steps, you see about 900 grains have been reoriented out of, I think it was 1800 or 1900 grains that were in the texture. About 900 grains have been reoriented. These are the number of the volume fraction that falls in the cells with different Schmidt factors. So this is essentially what was used to build those bar diagrams that you saw before. So again, here is the definition of the Schmidt factor. If you look now at the twin variant statistics, there are two pieces of information. One is what is called the selection frequency. The selection frequency means in each step you are picking a certain number of grains for reorientation. In each step you are picking a certain number of grains that meet the condition for reorientation. And then this tells you that 93% of those grains were variant 1, that 0.34, that 3.4% were variant 2, 3.4% were variant 3, and you didn't pick any grains that were variant 4, 5, and 6. So towards the end, this gets accumulated, and then by the end you have about 85% of the grains that you pick were variant 1, 10% of the grains were variant 2, 2% were variant 3, and the rest was 0 or negligible. This is telling you the volume fraction represented by each variant. The volume fraction has to do also with the volume that you assign to a grain, because this tells you only how many of these variants you pick. You pick so many variants, but it doesn't tell you if the grain was large or small. So in a way, this tells you which volume fraction twin for each variant, and that has to do with the weight that the grain has, or the volume fraction that the grain has. And so overall you have, if you add up all these, 0.42 by plus 0.04, this gives you 0.40, 46, 47. About, if you add this is the volume fraction that has to in total in your material, about 47%. So as I said, it takes some time until you get accustomed to make sense out of these statistics, but once you start getting into it, there is a lot of valuable information in this type of statistics, and as I mentioned before, a lot of this information is accessible to EBSD measurements. So you can then start comparing what you are predicting with which is the prediction of these quasi-statistical twin models, with what the experiment is giving you, and that's a good test, not only of the model, but because if you want to use your model for predictions, you want to make sure that your model works for a case that you can test experimentally. So it's a way of validating the model. And as a matter of fact, this is the last slide. I wanted to work to give you an example, but I didn't have time to prepare it. I started working on it because the code has this the possibility of doing thermoelastic deformation, and self-consistently. So you calculate elastic constant self-consistently, but you can also do a temperature change, and the thermal dilatation of your grains. You enter that, and then as the material cools or heats up, the grains dilate in the homogeneous medium, in the homogeneous effective medium, except that now the homogeneous effective medium is not viscoplastic, is a thermoelastic medium. So that is what is in the example one in your distribution. That is what is in the example one. And then what happens is if the surrounding matrix wants to contract in a certain anisotropic way, but the grain wants to do it in a different way, which is the case in many materials like zirconium, for example, which was the example that I wanted to show. Then that constraint is a very nice application to the problem of the HLV inclusion. It's a nice application to the problem of the HLV inclusion, where you have an eigenstrain, which is the difference between what the grain wants to expand and what the effective medium wants to expand. That difference has to be accommodated with stresses, elastic stresses in this case, and also a way of looking at what type of stresses you get, because those stresses you can measure experimentally also. You can do neutron diffraction or X-ray synchrotron diffraction and measure for grains that are oriented in a particular direction what type of stresses they are being subjected to. So those stresses can be measured and can be also compared to this. So I'm not going to go into this problem because I didn't really have time to do it properly. The only thing I want to mention is that in this case the process file will have also a certain number of steps, but those steps represent a temperature increment. In this case, you go from 900 degrees to 300 degrees Kelvin in steps of minus 50, so you cool by doing 50 steps of 12 steps of minus 50 degree Kelvin, and temperature is control. The control for the temperature is the variable number 8. So 1, 2, 3, 4, 5, and 6 is 1, 1, 2, 2, 3, 3, 2, 3, 1, 3, 1, 2. But variable number 8 is the control for temperature. And so in this case, as you can see, all of the strain components, except for the rotation of the whole rotation of your sample, which has to be kept fixed, you don't impose any of the strain components. They are going to be a consequence, and this is strain, not strain rate. They are going to be a consequence of the heating, and you do need to put something here as a guess to get started. But you enforce all the stress components, and you say that all the stress components are zero, because essentially you put this in your furnace, there is no stresses. You put it in your furnace, you heat it up, and then you cool and you measure, or you have it in your furnace and you heat it up and you measure as you heat up or as you cool down. Under those conditions, the stresses on the sample are all zero. There are no macroscopic stresses. So that is what the conditions look like. There is again, the only part of the single crystal file that matters here is this first 10 or 12 lines, really. Just the symmetry, the elastic constants, and the thermal expansion coefficient. As you can see, these thermal expansion coefficients for zirconium are very anisotropic. It says that in the basal direction they are 5.7, but along the z-axis they are 10.3. So that means that if you cool zirconium, it is going to contract twice as much along the z-axis than in the other direction. So if you put that zirconium in a medium that is kind of random, so the medium random wants to contract by the same amount in all directions, there is going to be problems, because the zirconium wants to contract more in one direction than the medium wants to do it. And when that happens, I'm going to show the results only, you develop high stresses. So this file, and I'm not going to go into it, this file identifies which crystallographic planes you are going to be looking at. You look at the elastic strain perpendicular to crystallographic planes that are oriented in different directions, which is what diffraction does. When you do a diffraction experiment, you have a grain in your material, and that grain will have a plane. Let's say this is your basal plane. There are going to be other grains that maybe have basal planes oriented in other directions, like this. If you throw if you throw X-rays into this plane will diffract them into a detector. And you capture the change in lattice spacing associated with the fact that there is an elastic strain. There is an elastic strain that changes the separation between the crystallographic planes. And so that is what you measure. That is a delta D over D, and of course this grain is not going to give you any diffraction into this detector. So only grains that are oriented like this or at small angle, because this detector spans an angle of about 15 degrees, only the grains that are within 15 degrees will give you diffraction. So you use that file that I was showing there. So you want to measure, for example, the prismatic planes and basal planes along a direction defined by these two angles. So maybe it is this direction, and along the direction by these two angles, which are the other two. These are polar coordinates of these vectors. And so you are really measuring subsets of grain inside your crystal, depending on how you orient your sample or where the X-rays or the neutrons are coming from. You are choosing only subsets of grain in your material to see what is the strain, the crystallographic strain perpendicular to specific crystallographic planes. So that information is very valuable. It is also a very high test for models, because now it's not the macroscopic response that you are trying to capture. You are trying to capture how a subsets of grain oriented in a particular direction are behaving inside your material. And for example, in the case of the zirconium, this is the zirconium that was used for this simulation. You see, it is extruded zirconium. The basal poles. This is the extrusion axis, the center, and the basal poles are distributed or like this. And that was compared again non-texture zirconium. So what you see here is the full lines are the macroscopic deformation of your sample. Your sample has no deformation at 900 degrees, that is your reference, and then you cool it down, you cool it down, you cool it down, and the sample contracts as you expect thermally. But all the three components, 1, 1, 2, 2, and 3, 3, all the three components coincide. They are all in the same, they fall all on top of each other. Now, an isotropic sample or non-texture sample is isotropic. So you expect that it is going to contract the same in all directions. But as soon as you give it a texture, you see that there is a split here between the axial direction of the sample, so this direction, contracts less than the other two directions, the radial and the tangential direction, which are the ones that coincide there. Now, the points are telling you what is the strain in the prismatic planes and what is the strain in the basal planes, the elastic strain. And as you can see, the prismatic planes are going into compression, and the basal planes, as you cool your material, are going into tension. Now, when you give it a texture, when you give to the material a texture, what happens in the radial direction, in the axial direction, is different. So it's not isotropic anymore. Now look at these values along the axial direction. The strains in the prismatic planes are of the order of 1.2, 1.3, 10 to the minus 3. So 1.2 epsilon O2 elastic is about 1.2 10 to the minus 3. So that is 0.012. Now that is a lot of elastic strain. For elastic strains, that is a lot. And as a matter of fact, what happens in this material, and actually I didn't put the experimental points, but we do have the experimental points for this measurement. You have in the basal planes, you develop stresses of the order of 100 megapascals in this material. And about the same in the prismatic plane. So the internal stresses are very high because of the cooling. Now there is a caveat. There is no plasticity here in this simulation. It's only elasticity. So you force the material to accommodate all the mismatch with elastic strains. There is some amount of plastic relaxation that takes place because when the stress increases, you activate some amount of plastic relaxation. But nevertheless, they stay more or less on these values, the internal stresses, and they are consistent with what is measured experimentally. Yes. So how are the sample axis? Okay. So you had that this was a O2 for figure, and essentially what you had was your your z-axis was, this is the axial direction, and this is the radial and transverse direction, and then you had something. I think we had something like this for the 1/1 2, 1/1 0, the prisms, which makes sense because if the z-axis is like that, the prismatic plane, if the z-axis is like that, the prismatic plane has to be perpendicular to it, so it falls over here. So this is the axial. Okay, the strings that I'm plotting is when yes, when those angle phi and theta that I gave are 0 and 0, you are orienting your sample, so you are measuring axial the strengths here um, of planes that are perpendicular to the axial direction. And when phi and theta are 90, well, 90 degrees means that are 0 and 90 degrees, so these are polar angles. You are measuring, in this case you are measuring planes that are pointing like this, and in this case you are measuring planes that are like that. So these planes are like that. The X-rays come like this and go like that. So you are measuring, I don't know if this, so in this case your X-rays come like this and diffract in that direction, but at an angle. So you have, imagine a stack of planes here, a stack of planes, you are measuring the separation, and here you also have a stack of planes, but now like this, and you're measuring the separation of those planes using X-rays. Yeah, there is no axial and transverse really. In this case, radial, tangent,
No.
and
In
axial.
the strain plots, strain versus temperature.
Okay.
So you have plotted one in black, the lines.
The
Yes.
lines. Okay, the lines are the macroscopics. Yes.
Yes.
So if you have let me see, if you have a sample, uh, if you have a sample and you cut that you have extruded, and then you cut a cube from this sample, which is what you are going to measure. This cube has oriented this facet in the axial direction, this facet in the radial direction, and this facet in the tangential direction or tangent direction. Okay? You cut this cube. So that is what I call radial, tangent, and axial.
Okay.
And now you are either measuring planes that are parallel to this, either basal or prismatic planes, or you are measuring planes that are parallel to that. So planes that either planes that are stacked like this, or planes that are stacked like that. And you're measuring the separation of these planes. Depending on the wavelengths, you pick the basal or you pick the prismatic because of the yes. If you want to work on the twinning problem, twinning of the zirconium, I mean I'm going to be here until 5, or even a bit more if you need to do consultation. So if you want to work on that problem of the zirconium, we can work it together. I don't know. Or if you want, I suggest that you try to run, in addition to the in-plane compression, some of the other cases to check the. And you can also check what happens if you use the volume fraction transfer law, uh, which is the I I twin. I think I call I twin model or equal 3 in the single crystal file, identifying the identification for the twin. That is the volume fraction transfer, because in that case you are going to be creating a second phase, uh, which uses actually it uses a feature of VPSC, which is the children are considered are treated as a second phase, really. So when you read the input file for that particular case, you have to read the parameters for the parent and the parameter for the children. They are the same because the children are going to be the same material and they have zero volume fraction to start with. But you are going to be running really a two-phase problem. I have one where I put a mixture of zirconium and uranium just to show how the thermoelastic behavior is. So I picked so in this case there are two phases now, and each of them has zero point 0.5 and zero point 0.5 relative volume fraction. So I read all the parameters for the phase one, which is the information about phase one here, and then see there is also information about phase two. So essentially all the parameters that you read for a single phase, you will read exactly the same ones also for the second phase or the third phase, how many phases you have, and then the code will build up the polycrystal using the texture that you declare in those phases. No, but no, I don't have here I don't have an example with the volume fraction transfer. And by the way, if you happen to be running the code later, and you can contact me about issues that you find. I mean, if it is something relatively straightforward, I can provide some support. I mean, we don't provide support for solving research problems, because then that means more time. But sometimes the problems have to do on how to enter information, or can I solve this particular problem, or how do I pose my boundary condition for solving this particular problem, that kind of thing. You can always contact me, and I will be available. I don't know if you have my email, but my email is tome at lanl.gov.
So let us thank Dr. Tome for a very nice set of lectures over the last 5 days. And
Thank you.
I think, as I was telling you that most of the VPSC users that we have in India, they mostly use the Voce law and do not know much about the formalism or how it works. So this set of lectures has been very useful in that sense, that people, the students, the participants have learned not only what goes on behind the in the background, but they have also learned many different applications and all the other different constitutive models that exist.
Yeah, we couldn't cover all the models that are in the code,
Yes.
but some of them.
Yes. And of course, those who are more curious, they can go and explore and find all the examples and also read the book once it is out. Thank you again, and
Well,
I
no,
think,
thank you
yeah.
guys. It was a good opportunity for refreshing these lectures, because this is something that I have done several times through the years, but now with the coming up of the book and the streamlining of the code and some of the results, there are new results, there are new constitutive laws, and so this was the first opportunity to really expose what those in a course, no? So it was some work to dust up the old slides and put them make them consistent with what is in the book, but it was good, and I, uh, I enjoy doing this. So I hope you find it useful.
Thank you once again.
Okay,
Yeah.
thank you guys.
Yeah.